Okay, hi everyone. So welcome to
Hey
our
everyone.
second last session. And for this session, we are going to be talking about joining different data sets. Tomorrow, in our last session, we will talk about an overview of how you should prepare yourself for the start of the UN Datathon. Again, I'm Ali Rizvi, and I have Shobit Nair with me as well, who will discuss the key libraries for joining datasets. So this is the list. On Wiki, you can now go and see all the various recordings from any sessions you might have missed. On the UN Datathon Wiki, you will find all the previous recordings as well. During the Datathon, we will be available via Discord to help you with any sort of troubleshooting or any issues you face, basically. So I want to give a quick refresher of the key concepts that you need to keep in mind for the rest of this session. And again, the purpose, as always, is so that you can have a great datathon experience and you are on your journey to becoming expert data scientists, and so that we can help you understand and find insights from data without compromising privacy. So I created a few, based on the questions we have been receiving so far in the sessions, I created a bit of a visual diagram to help everybody kind of get on the same page. So in normal data science or usual data science, basically you have access to a data set, you can see everything, you can see all the rows, all the columns, all the numerical values, and you just use your normal algorithms to interact with the data. You use your normal pandas, NumPy, etc. Right? But what happens is when the data is secured in an enclave, when it is very sensitive data or when it is non-public data or the team doesn't want to reveal the private data of individuals, to the world. This can be health data, this can be banking data, this can be all sorts of data. This can be a corporate information that is not public, for example. And that data is basically secured in an enclave. And now we enter the realm of privacy enhancing technologies. Now, as a usual data scientist, you can no longer interact with the data anymore. You can't use your normal pandas. You can't use your normal kind of functions. Now you need privacy enhancing technologies to interact with data that has been put in an enclave. So the special kind of algorithms that you use in Python, etc., that's what we are talking about in all these sessions. The privacy algorithms to interact with data that has been secured. And by doing that, you are now not a usual data scientist, you're a responsible data scientist. Now, the question is, okay, but what is the cost of this kind of lens that you're using to look into the data? What is the cost of this type of privacy algorithm? How is the access basically to the data managed? Because we said, okay, the data is secured, but you are still interacting with it. So, what is this interface, and what is the cost of this interface? So if you think of this magnifying glass analogy for a second, basically what this lens is that it's like a clear to blurry glass, basically, that we are putting on top of the data. And the more clear lens you want, the more expensive that lens is. And that cost basically of accessing or this nice lens is dependent on what level of detail you want to see in the data. So for example, you can see this strawberry. Now, obviously, the strawberry has little dots or seeds on it, right? If the glass is very clear, you will be able to see all the seeds. You will be able to count all the seeds. But if the glass is a bit blurry, you can say, okay, there are some seeds, maybe there are 100 seeds, maybe there are 150 seeds, I don't know, but I can see there are some seeds, and I can see that it's a strawberry. And basically that's the kind of concept that the more granular information you want, the more epsilon it will cost you. And epsilon is just the term to keep track of how much visibility you have on the data. Now, uh, when privacy teams share that data, they don't want you to access all the, granularity of the data. That's why they have taken all these measures to put the data in a private space. And so the data sharing team can put an upper limit. Like they say, like, even if you spend a lot of the epsilon, we sorry, don't let you see the 100% of the data. So this level of visibility you can't buy from us, right? And this basically is the concept of an epsilon budget, that you have some limitation on how much clear glass you can buy to look at the data. Now the question becomes, okay, so how much epsilon should you be spending on or to look at the data? How do you decide? Do I need a blurry glass? Do I need a very clear glass? And that really depends on the kind of question you want to ask from the data. So here, the kind of blurry cars picture that we have been using in the last few sessions, you can see that they're all the same pictures. They're just different. You're looking at them through different epsilon conceptually. This is like the cheap glass you're using, not too much epsilon, and it's very blurry picture. Then here you're spending a bit more epsilon, so you have bought a bit nicer glass, so now you can see a bit more details. And this is the really expensive glass, you can see everything. And of course, this determines what kind of questions you can ask, right? Like, so in the blurry picture, you can say, is it night or day? Yeah, you can already tell it, even though it's such a blurry picture. Is there a big tiger in this picture? I'm pretty sure you can all tell me, yeah, there is no tiger in this picture. Is there a car in here? And you can say, yeah, I think there is a car in here. You can sort of make out the outline of this car. Now, when you spend a little bit more epsilon and you kind of buy slightly less blurry glass by spending more epsilon, because less blurry glass is expensive, you can say more. You can ask more complex questions. You can say, okay, how many cars are in here? How many red cars are in here? You can go to more detail. And then when you have 100% of the data, when you have like all the thousands of epsilon you have spent, you can ask very private questions. You can be like, is my brother's car in this picture? Is my husband in this picture? Or you can ask very detailed questions. But of course, because we are doing privacy, the team doesn't let you have this level of visibility. You can't buy this much epsilon. You can't look at all the data. So you are limited to some extent on the questions you can ask, because now the data has to have some security. And so just a rule of thumb, right? Like, so rule of thumb is, if you're doing summary statistics, you're doing basic operations, you can spend really small epsilon, and that will be fine for the mean, average, max, min, various bounds. Basic operations, very small epsilon, 1, 2 epsilon, more than enough. 0.1 epsilon even for some functions you can use. Now, when you do fancy stuff, you do machine learning model training, you want to do data joining, you want to do all the stuff that Shobit is going to talk about in today's session, you need a bit more budget. You need to pay a bit more, because the model needs to have a little bit more visibility into what the data is and the kind of stuff that is available in this data. So that's kind of the main concept here. And then, so the important thing to remember is that going back to the kind of responsible data scientist view, right? So when now you want to look at the data in the secure enclave, basically you say percentage AG. You're using your Python. We will look at this in more detail. But basically, when you say percentage AG, please do XYZ operation on the data, and please use this specific level of epsilon that I'm telling you. And then it will go and do that operation on the data, and then you can export the results of the operation back into your local environment. And so the main important thing I want you to remember is that when you do percentage AG, that's basically your secure enclave interaction. So when you think secure enclave, think percentage AG, and any cell that starts with percentage AG is being executed in the secure enclave. Those functions are the private functions. They need some epsilon budget to be done. And then once you export the results, export the kind of summary statistics or whatever model output, that's going to come to your local environment. And that's the main key takeaway, that think when you want secure environment, that's percentage AG. When your local environment, you don't need percentage AG. And The session privacy odometer thing we talked about yesterday extensively as well, that this is a way to keep track of your wallet. It's a way to keep track of your budget. How much epsilon do you have left in your budget? That will tell you. And so you should be doing that again and again. And so that's the summary. Hopefully, all of that makes it very clear now that like what is epsilon, why are we using epsilon, and basically what is this kind of conceptually how you can think of epsilon. Epsilon is basically like the lens that you have to look at the data, and the less blurry lens you want, the more epsilon you have to spend. Like clear lenses are going to be more expensive, whereas the little bit blurry lenses are cheaper. So less epsilon needs to be spent on them. And the rule of thumb, as we said, is basically that simple operations, you don't need to spend so much epsilon. You can spend small amount of epsilon because you can still do a lot with blurry picture, blurry data, or private data. And when you need a little bit less privacy in the data because you need to do a lot of you need the data to be accessible a bit more, then you have to spend more epsilon. And that is the machine learning type of stuff needs a bit more epsilon. So I'll pause there. Any questions on this so far? Okay, so I will keep going then, and hope if you have any questions, you can basically then keep posting them in the chat, and we will keep addressing them. So now I'm going to ask Shobit to join, and then we can go from there.
Yeah, sure. I'm audible?
Yes.
Okay, cool. I'll just share my screen. Yes, sir. Just give me a sec. Zoom requires some security measures in my OS, so I'm just giving it the
No
access.
worries, no worries. Yeah, so meanwhile, participants, what you can do is to follow along Shobit, please go to antigranular.com and open the notebook that Shobit is going to do the follow along on. So if you kindly basically go to antigranular, there you can, and please log in. From there, if you go on notebooks, Shobit is going to be walking along on two notebooks. One is the record linkage notebook, and the other one is going to be the SP link notebook. And so you can just open the relevant notebook and you can go from, and basically you can copy the notebook to your local environment as well, and that will open it in Google Colab, and then you will be able to follow along everything. Shobit, is it all set up? Good to go?
Yeah, I'll need to try to share my screen. I think
Sure.
I have to, yep. Let me know if it's visible.
Yeah, we can see the Zoom tab.
Yeah, okay.
So, awesome. Yeah, perfect.
Okay. So guys, today we'll be talking about basically how we can responsibly link data sets. So till now, in all the sessions we discussed, we are just concerned about one data set, but there are high chances that we might need to do analysis where one data set might be linked to another data set. So for that, we currently have two libraries. One is record linkage. So let's just pop into the docs. So in the private Python section, you can see we have SP-link and record linkage. So these are the two libraries that we use to link data sets on some fuzzy matching conditions, compare rules. Then we have features which can index the data sets. So these two libraries are mainly for that. And these two have differences in how they work as well. For example, record linkage gives you more control on how you need to set up the compare rules and how the internals work. But SP-link is more of a probabilistic method of how you can link the data sets. So to start off with, we'll just go through a beginner to advanced guide on how you can work with record linkage. So in the antigranular site, you can go to the notebook section and you'll be able to find the first notebook, which is Mastering Privacy First Record Linkage, a complete guide. If you have already logged in, I think you'll have a button here which says launch the notebook, which will direct you to the Google Colab. I'll just give you a few minutes to actually do it. So basically in the notebook section, just have to move to the first notebook, which is Mastering Privacy First Record Linkage, and then the launch notebook button. Okay. Just give like a confirmation if you're already into the notebook. Or if you have any issues like accessing the notebook, do let us know in the comments. Okay. So first, what we need to do is just connect to the anti-granular client. So we do pip install anti-granular, and since we are actually comparing with the actual record linkage library in this notebook, so we will also need to install the original library, and I'll be showing you how the differentially private version works alongside the original version. So let's let the libraries get installed. And meanwhile, we'll just give a hands-on on what record linkage is and what all we will be covering in this notebook. So mainly we will be covering like what is indexing and how you should use indexing in record linkage. What are the various compare rules that are allowed in record linkage, and how you can actually use the compare rules that you set up to create a linked private data frame. And once you create that linked private data frame, you can do all sort of differentially private analysis on that. Okay, cool. So to connect to the antigranular client, you need to just go to the notebook, click on this sandbox for Harvard OpenDP button, and you will have your credentials here. And this will only come up if you have already logged into a platform. If you haven't, it's better if you sign in using an email ID or Google. So once you click that, it gets copied to clipboard, and you can just paste your client secret ID to connect to the anti-granular. Let us know if you have any issues so far. Okay. So what is the sandbox competition? So basically in the sandbox competition, we have two data sets. One is the flight company data set, and one is a health organization data set. So they both are linked, and our problem statement was to predict or basically inform which all flight IDs might have a patient who might have COVID or like who has been tested COVID positive. So that was the main problem set. And to analyze that, we will be actually linking the data set, filtering it on using some conditions, and giving the result out. So this notebook is mainly to just give you a record linkage hands-on, and not to give you a depth on how you can create, like solve that problem. Once we cover this, we will be actually covering the notebook, which actually solves the problem statement that is just say. So these are just some utility functions that I'm setting up locally, which will be used to plot graphs and stuff like that. So if you see, we have two data sets just for our reference, with ID, names, and country. And if you see, there are some names that are similar, but not exactly similar. It's so there are high chance that when two data sets are formed, there can be typos in names, there can be word shufflings in addresses, there can be differences in the format of the dates that are set up in different data sets. So you need some kind of fuzzy matching to actually link both data records. So that's where record linkage actually comes in. So here we're just setting up the data sets locally, and we'll be actually private importing them onto our anti-granular server. So this is the opposite of export. In the export, you actually get information from the server to your local environment. But in a private import, you're sending information from your local environment to our AG server. So first, let's cover what is pre-processing and record linkage. So for pre-processing, we have majorly two functions. One is a clean and another is phonetic. So in the pre-processing, this clean is very much similar to the clean that's available in pandas, in which you can clean strings based on various conditions, regex, or basically remove, like you can probably remove the Mr. out of Smith. A lot of cleaning mechanisms can be done, mainly involves string manipulations that you can do before you actually do the linking. So mainly you gotta clean the data set before you actually set up the blocking rules and compare rules. Similarly, we have a phonetic mechanism, which uses soundex to actually give a sound encoding of what, basically how that word is pronounced. So if you check, there is Smith and Smythe. Could be pronounced as Smith, but based on the soundex, both have the same phonetic encoding, which means that this could be a potential typo when someone, let's say you go to a clinic and you say Smith and he just types SMYTH. That could be the kind of issues that can come up when you have two data sets from different organizations. Let me know if you have any queries so far. So what we have covered so far is just the pre-processing, nothing more, the clean function and the phonetic function. Yeah, sure, Raj.
So I was curious, here when you said that you're checking the phonetics, I'm curious, like if two people have the same name but writes a different way, they would still be considered as the same person, or is it just processing it such that two names are considered as the same name, but they might have their unique IDs?
Basically, in this case, it's basically we can give a method. Let me go to the docs. That will help in a better way. So basically, the thing is that for the method, we have like various mechanisms like soundex, ISIS, metaphone. These are
Yeah.
various ways in which you can encode a string to a
Okay.
particular code. So as I said, the Smith and can be written as SMITH or maybe written SMYTH in different places.
Right.
And when we say it, it might have the same phonetic encoding.
Right.
So
But
that's what we are doing. So it's we need one way in which you can match two strings. So phonetic encoding could be a way. It's not like a guaranteed way. It's like a probable way.
right, but I was curious, like, is it matching like the same people from one data set to the other data set by doing this, or
No, We are just sending this array. For
Okay.
now, we are just sending this array and we are just finding out their phonetic encodings. The linking process is done later.
So this two names, you are just harmonizing it such that always Smith will be pronounced one way. Like that's the thing I guess I'm getting a little bit confused. Like, are you harmonizing like the word Smith for all the Smiths in whichever way it's written? Like if it is written in
Yep. In one way,
okay.
yes. Yeah,
Okay.
I'm trying to get all Smiths in the same encoding.
Okay, gotcha.
Yeah.
Okay. So thank you.
Yep. Perfect. So yeah, phonetic encoding is one way in which you can actually encode strings into their phenomes. Similarly, we can go to, once we are done with the cleaning, the first step that you do in record linkage is indexing. So there are like, we have like in depth written like when you should use it and how you should use indexing. The main purpose of indexing is to reduce the computation for comparing records. So let's say we have a data set and I index based on, let's say, a citizen ID. Now the citizen ID is a unique for everyone, so the indexing becomes easier. I can also index on date of birth. The collision of date of birth is also fairly low because you could ask me, isn't citizen ID more unique, right? The issue with just blocking or basically just indexing citizen ID is that you won't be able to link two records easily, and it's possible that in one data set citizen ID is there and the other data set the citizen ID might not be there. So you need to come up with an indexing that's there in both data sets. And if we also handle the case where you don't find any common attributes either. So there are like multiple ways of indexing. One is the traditional full indexing. So what full indexing does is that it basically links every pair, or basically it forms every pair possible. So if you need to visualize, it's something like this. So we have like 5 records in the left and 5 records in the right, and it will link everyone with each other. This is mainly used if you have like literally no idea about the data set, like how you should link it, or if the size of the data set that you're trying to work on is really small, that you can afford the full indexing. So if the size of the data set is in the order of hundreds or thousands, you can surely go for full indexing because it's computationally viable. Yeah, so when to use it, small data sets, absence of common attributes, and you need to kind of maximize the match opportunities. So these are the scenarios when a full indexing is good. So, but obviously the data sets we receive are generally not small and are huge. And that's where you cannot actually use full indexing. So we come up with something called as block indexing. What exactly is block indexing? You can consider it as the normal indexing that any database kind of does internally. So let's say you can index based on some particular column. So let's say we can index on date of birth, we can index on postal code, we can index, maybe a custom index can be made on, let's say, index people with their initial letter. There are a lot of ways in which you can block categories, right? Is so far so good? Full indexing, block indexing. Full indexing is all pairs, possible pairs, basically. And block indexing is you choose what kind of attribute you want to block to. So let's say I use block indexing on the country. So we will have like links across people having the same country name. Like everyone from US will have a link between each other. Everyone in maybe, let's say, India will have a link between each other. That's how block indexing would work. And in case you want to block across, like do a block across multiple parameters, you just have to keep adding more indexings. That's all. So in this scenario, we were blocking on the names. So if you remember, we had the name something like this. The array was something like John, James, Arthur, Raj, Kenny. And similarly, we have Raj and let's say Arthur here in the second data set. So these are the only two where they can actually get a link. So Arthur here from the first data set will link with the Arthur in the second data set. Similarly, Raj in the first data set will link with the Raj in the second data set. So graphically, if you see, block indexing would look like this. Basically a link between common blocks. So far, so good. If you have any queries, let me know.
So quick point, Shobit. So basically, the other thing is right, like that the Smith thing that you were mentioning previously. Of course, that the two Smiths and the Smith, it's hard for us to know without any additional data that whether it's a spelling mistake or is it actually two different people using two different name spellings. And so for that, obviously, we will bring in more of the columns to make more unique indexes, correct? Like we will bring in their
Yeah.
last names or their date of birth or their email IDs. And that way you can start separating, because even as a human being, if I just, told you, hey, here is my friend Smith and here is my friend Smith, and you won't be able to know if I'm talking about two different people or one, and you need more information. And similarly, the model also needs more information to create the correct index. Hopefully that adds a bit more clarity to the question before.
Yep. So for example, in this, we just use the names for the blocking. So let's say we add the country as well. So now we are allowing candidate links with the same names as well as the same country. So we are actually expanding our links, because the first step is to actually set up the links, like the probable links, before we actually start the comparing them. So first step is cleaning, then we go on to indexing, then comparing, and then we actually create the linked data set. So these are the 4 steps that we go to, which kind of completes the record linkage library. So we are done with the cleaning. With respect to indexing, what we potentially want is to index it such a way that we don't lose potential matches. It's okay to cover some extra record matches, but definitely we don't want to lose the matches. So that's how you should try to block or put indexings. So if you see in this one, we are probably losing some matches because we kept a strict indexing on the name. So even if there is a typing mistake, it's messed up. You will miss it out because it doesn't exact indexing. Similarly, for the country, we can just block on the country, and now you can see that there are more links that come up because there are more people with common countries. So we are just kind of relaxing our criteria now, just so that we can accommodate more links. Okay. And in case, like, if you have minimal idea of how you can link two data sets, let's say you have a data set 1 and data set 2, and there isn't any concrete mechanism in which you can actually apply a linking, indexing, let's say a common attribute, but the data set size is huge, let's say. In that scenario, it's sure that you cannot use full indexing. So random indexing is something that's more useful in that case. And this is also really good if you need to actually kind of benchmark your current solution against some method. So in this scenario, we are just indexing on random. We just pass on how many links we need, and it will just randomly assign links from dataset 1 to dataset 2. So we basically have 10 links from DFA to DFB in this. So this pretty much covers in what indexing is. And if you have any queries on what indexing is, let us know now. Once we are done with that, we'll just proceed to how we compare.
Just a quick question. So like, can we do the next step without indexing, or is it important to do indexing first and then the second step?
Yeah, so to do you need to do indexing because the compare step actually needs the probable links as an input. So you need to actually do the indexing step so that you can get what all links, basically what all pairs should I run the compare on?
Right. So then indexing is basically making is a sort of pre-processing step on two different data sets. And it is not, this indexing hasn't joined it in any way. It has sort of assigned that maybe when looking at these two data sets, these two things could be similar. And so that it allocates them some kind of index. And then the second step of compare will actually do the proper quote unquote join or matching.
Exactly.
Okay.
Okay. Moving ahead to comparing. So in comparing, there are a lot of ways in which you can do stuffs. Like one is the exact matching, but that doesn't give a lot of advantage to us because you could pretty much do an indexing on it. Then we have like fuzzy matching, then numeric date comparisons. And the best thing about record linkage is you can put up custom comparisons. And that is something that's missing in SP-Link. So this is the major advantage of you trying to use record linkage over an SP-Link, which is you can set up your own custom comparables. So we'll be working out with a large data frame for this compare mechanism. So let's say we have two data sets, which is the DFA, a large DFA and large DFB, which contains a lot of informations like street name, address, suburb, postcode, basically census data. Similarly, DFB, and these two are related in some sort. So we'll try to actually first kind of set up a basic indexing rule on them. So we are basically indexing them on date of birth and postal code for now. And once the indexes are made, we will basically obtain the links, which is obtained here. So if you run this, we'll probably get how the links look like. So let me just quickly run few cells so that we can actually see how it looks like.
Shobit, while that happens, what is the cost of the indexing step? Does it have a strong epsilon cost that I need to give?
For indexing, nope, you don't need to do, you need for the entire record linkage step, you don't need to spend any epsilon because it happens internally and you're actually not obtaining any information. You're just trying to experiment based on like what you're trying to, like basically you're just experimenting some conditions and you're creating a data frame. Once you create the data frame for getting information from that, you need epsilon.
Got it. Okay, so we can do a lot of indexing and we can try a lot of techniques in indexing without spending any epsilon.
Exactly. So let's run this out. So I'll just add a new block and just print the links. And this, mind you, this is running locally. So don't mistake it being run in AG server. So this is how the links look like. So once you are done with like blocking, setting up the correct blocking rules, you get a lot of links. And in the AG server, you cannot actually print the links because it's private. But locally, I'm just showing you how it internally looks like. So it in AG server, it's like a pandas private series with a tuple.
So how did you get it into your local environment without using export?
Oh, so initially, as I said, the first step was actually setting up the data sets locally.
Yeah.
Yeah, a lot of everything was set up locally, like the DFA, DFB. So the large DFA and large DFB are is from inbuilt data set that record linkage provides.
Got it. So then, but you did the indexing in the local environment or in AG?
Oh, I'm doing in both environment to show how they compare with each other.
Ah, okay. So that you didn't have to export the linking. Fine, got it, understood.
Yeah.
But
Exactly.
otherwise, if we did it in the remote environment, we will need an export step at this point, and then we will be able to, yeah.
Yep, sure. So exact compare rule, as the name suggests, is basically doing an exact matching. And this should only be done as a filtering mechanism if you're like pinpoint sure there cannot be any error. So it could be most probably something like as probably some citizen ID, or basically a company ID, or anything that's very unique, and the chance of having it as an error or having like noisy data on it is fairly low. So in such cases, you can use exact compare rule to filter your links. So this is how basically the code would be like. So you set up exact, we set up first a compare method, which is compare equal to rl.compare, the record linkage.compare. Then we set up the mechanisms on which we need to apply the exact mechanism on. We have left, right, and labels. So left means the column ID in the DFA, right is the column ID in the DFB, and label basically means the label that you need to assign for the resultant feature you get. So to visualize, it will look something like this. So I'm just running this locally to show you how it internally looks like. And mind you, these stuffs that I'm showing you is a private data frame, and you won't be able to easily access it. So in anti-granular server, you can only get informations like differentially private aggregates like mean, sum, etc. So for example, I'm just, once the features is made, I'm just trying to obtain them using a mean, sum, etc. So I'm just printing what is the mean amount of exact matches that happened across different features that I said, basically attributes that I set up. Any confusion so far? Okay. So what does this features matrix mean? Basically, what this means is that for the compare from that record 0 and record 0 dupe, the social ID, name, and address is matching. So the features matrix is kind of matrix that you get based on the compare rules that you set. So I set a compare rule for social ID, I kept a compare rule for name, I kept a compare rule for address. If they match, it's a 1. If they don't match, it's a 0. And you pass in the links here, and it basically does that. It basically runs the compare rules against those links, and this is a feature that we obtain. And based on the features that we obtain, we decide how we need to link the data set. So we can figure out more once we move ahead. So we have like a lot of various other rules like string with multiple string matching algorithms. Similarly, we have numeric comparisons, which compares two numbers based on various algorithms that you need to set up. So before I think deep diving into this, we can just look onto a very simple example, and that is sample example using, just give me a sec. Yeah, a very brief example of how the record linkage is used for the sandbox hackathon. So for the sandbox hackathon, if you see, the problem statement was to actually find out people who are tested positive, and we need to inform the flight IDs of. Can you actually come up with the problem statement again, Ali? I think I'm a bit confused with that.
Say that again.
Yeah, could you actually come up with the problem statement that we had for the Harvard hackathon?
Yeah, so basically, what we are trying to do is that this is showing the track and trace problem that arose during COVID, that obviously people were getting COVID, and if you need to inform that you have been in touch with somebody who was infected with COVID, you need to figure out a way, okay, how are we going to track and trace the people? So in this, there are two data sets. One is from the flight companies who are obviously knowing which people traveled on which flights. And the second data set is from the health organization, which tells you the results of COVID tests from different people. Obviously, both data sets may have some overlap of people, or some people did COVID tests but never took a flight, and some people may have taken a flight and never did a COVID test, etc. These informations need to be shared with some privacy, because of course you don't want all of that type of travel information to be given to the health organization, and the health organization obviously doesn't want to give the health record to the flight company. So that's the motivation behind this, that we need to come up with a way of joining these two data sets and informing passengers that, hey, somebody on your flight tested positive for COVID, so please quarantine. But we want to do this without compromising privacy of any of the individuals in both data sets.
I see. Yep. So in this example, it's a very short example on how we try to achieve the problem statement. So what we basically do is that since we are done with indexing and compare, we'll be able to figure this out more easily. So we first load the two data sets, which is the health and flight data set. And I'm just printing the columns to actually see what all column informations we have for each data set. For the flight, we have the number, date, from, to, the passenger first names, last names, and DOB. Similarly, we have it for the health data set, and the only common information that you see are these three columns in both of them, right? So I think we need to come up with some way in which we can link the data set based on these three columns. So what we try to do is, first, we filter those people out which are tested COVID negative. Like, we don't need those people. So we kind of only accept those people who are COVID positive. And we kind of drop the columns which do not satisfy this, records that do not satisfy this condition. And now our health data set that we have to only include the people that are COVID positive, as you see. So once we actually pre-process this, now we can set up the indexing rule. So for indexing rule, what we set up is basically a block rule against the passenger and the patient date of birth. So as I said, first name, a block rule should only be used against information that has less chance of having an error. So passenger date of birth is something that's generally common and has a like the chance of having it different in two different data sets is fairly low, unless they are in different formats. So you could say that in one data set, the format could be like MMDDYY. In the other, it could be DDMMYY. So in those cases, what you need to do is that, and during the pre-processing stage, you kind of need to normalize all of them, or basically bring all of the formats into a uniform form. So that's a pre-processing that you should do. But in this sample data set, both had the same format. So we actually didn't get involved in doing that. So once we block it, we'll just try to count like the number of links that we obtained. So we see that we obtained around 6,000 links. So earlier, the data set was like health records were 59,000. Total flight records were 39,000. After filtering the people with COVID positive, the total health records, the differentially private health records, are like around 1,200 to 1,300 people. And then we just apply the date of birth blocking, and we have around 6,000 links. So let's set some compare rules. Since now we have the links of people that are probable matches, we will try to further refine it. And that's where the compare mechanism comes up. We try to further refine the links that we have obtained. So we have set up 3 compare rules. One is a string compare for the passenger and patient first name, and a string compare for passenger and patient last name. So what does this algorithm do? This algorithm kind of returns a weighted cost from 0 to 1, depending on how much they match. And similarly, we have also set up a custom compare rule. And what it does is that we only want to accept those links in which the date in which the passenger actually traveled was at least within 14 days in which the date the patient actually tested positive. So we only want to inform in such cases. So we actually keep a custom compare rule, which actually kind of sets a criteria that if the date is within that criteria, then only accept this link. So these are like the custom compare. This is the custom compare rule that we set up. And the string compare rules are against the first names and the last names. If you have any confusions, let me know so far. Okay, so as we discussed, when we set up the compare rules, we basically have like the 3 compare rules against the first name, last name, and the date. So if you see, there's like a weighted kind of cost that we obtain based on each link. So for link from ID 28227 to 48703, the first name matches to like 0.4. The first name matches for like a 0.88. So it's basically like the cost that the algorithm returns us based on the matching criteria that the algorithm uses. So the algorithm we used here was Jaro-Winkler, and based on that, there are various other algorithms that you can use. Jaro-Winkler is a bit more relaxed. There are some algorithms that is a fairly more strict compared to how they fuzzy match. So we have discussed that in the in-depth notebook, but for now, let's cover up the brief one. So once we have this cost set up, what we need is a threshold value in which you need to set up a match. So what is a threshold value? Threshold value basically means that I kind of sum the first name, last name, and the date CMP. And any link which has its sum greater than the threshold we keep, the data frame will actually be formed using those links. So what I do is I kind of find the average weight, or basically the average cost based on this feature matrix, which is I'm taking a sum across horizontal axis and taking a mean of them. So we obtain that there is like a 2.4. That's the average matching cost that's between most of the candidate links. So based on my hunch, what I feel is that something around 3.1 is a fairly strong match. You could even describe this data set and see like what are like the values you obtained on different quantiles rather than mean if you want. So if you want like a 90% quantile value, you can just do something like features.sum.quantile q equal to 0.9. Then that will give you the weight of the 90th percentile. And maybe you can set that up instead. So all you need to do is once you have obtained the cost, just need to use the compare method, compare.getMatch method, and give the threshold, which will create the linked data frame out of it. So this is like a very brief example in which we kind of covered only through the indexing, some brief compare rules and custom compare rule. So obtaining the linked data set is as easy as this. Like you produce the feature matrix, you kind of try to find what is like the average cost or like the threshold value that you need to set up for the linking criteria. And then you just call compare.getMatch with the threshold value that you desire. And you will obtain the linked data set, which is a private data frame. So this pretty much covers this brief notebook. So let me know if you have any confusions so far. Is there any step that you felt like difficulty in understanding? Let me know. I'll try to explain more on that. If there's any part like indexing or compare, or how the data set is getting linked, anything that's confusing for you.
So just being mindful that we are almost coming to the end of the time of the office hours. So guys, if you have any questions, feel free to ask on the Discord. You can email us, you can check out the docs. An important thing is that tomorrow in the office hours we will actually have somebody from the FAO team. For the pet track, the data set is coming from FAO, which is the UN arm which deals with agricultural data and food security data, and they have provided the PET data set. And so we will have one of the chief statisticians from the FAO team who will be answering your questions on what you can expect from the data set. You can ask them questions about the theme itself. As I mentioned, the wiki has all the details about the FAO data set now. You can go and look at what kind of was the survey mechanism for developing this data, what are the some fields in this data, what kind of questions you can ask from this data. So I would encourage you to look at that today or tomorrow before the office hours so that you can ask the relevant question to the relevant person from FAO team. Yeah, and I think maybe Shobit, we wrap it up there. So thank you so much for taking everyone through these two notebooks and for the detailed explanation. And thank you everybody for joining. And hopefully we will see you tomorrow. And yeah, please stay tuned and get in touch with us via Discord if any questions pop up. Thank you, everyone.
Thanks a lot, guys. Have a great day, evening, or afternoon, depending on your time zone.
Thank you, Ron.
Take care. Bye.